Okay, so now I feel good about moving on to some of these bigger atoms now that I don't have to write the full electron configuration. So let's move on to the next one, the one that comes after argon. Argon is here, so we have to go all the way back to the next row to potassium, which is K, and potassium has 19 electrons. So we'll go ahead and use our new notation here. We can adjust it when we get there. So we'll just take argon, which was neon, 3s2, 3p6, and we need to add one more electron to it. So let's check our picture. We should have 19 electrons in the picture, and right now we have 8, so we'll do a speed run. 9 would double up here, 10 would double up here, 11 would move up to the third shell, and 12 would doubly fill that subshell. 13 would move up to the P subshell in the third shell. And we start doing our single occupation. 14, and then 15. And at 16, we start to double up. 16, 17, 18. And so now we need to place the 19th. And so our logical conclusion would be we should fill all of the third subshell orbitals first, and we should put that 19 electron here. But there is a spoiler that is incorrect according to experimentation, because there is a secret 4s orbital that is actually lower energy than the 3d orbital. And I'll pause here for your mind to be blown. I know this isn't what we agreed on when we wrote the rules, so we're going to just have to write a new rule. So this Aufbau principle, where we said we filled the lowest energy first, is still true, but this bit about the lowest n is not always true anymore. That didn't work out for us when we were trying to write the configuration for potassium. So let's add a rule here to talk about that. And that rule is going to say, follow the experimental filling order. So what happened was we made this prediction. We made this prediction that we should fill all of the electrons within the same shell with the same number out front first before moving on to the next shell. But according to experimentation, scientists discovered that some of these higher energy orbitals were so close in energy that they actually started to switch order. And some of the higher principal quantum number orbitals ended up getting filled experimentally before some of the lower principal quantum numbers. And so this is the true filling order. You can see that not all of the ones are together, all of the twos are together, but for the threes, they start to get separated. This 4s squeezed in the center. And for the 4s, one of them is over here before the 3d, and the 4d is over here on the other side of 5s. So it gets a little bit complicated, and I really do not recommend memorizing this filling order because it is just not a good use of your time. So there are two memory tools that I will propose for you to use instead of memorizing this giant list of the experimentally determined filling order for the orbitals. So memory tool number 1, you may have seen in high school if you talked about this. And that memory tool is basically by writing the names of the order in a particular shape to help you remember the filling order. So there are a maximum of 8 known s orbitals. So we write a vertical list of all the s orbitals. Then we write a vertical list of all of the p orbitals, remembering that there is no 1 p orbital. It starts at 2. And then we add a column for the d orbitals, remembering that they start at 3. And just for the sake of completeness, we will even add a column for the f orbitals, just a couple of them. And the way we use this tool is we're going to draw diagonal lines through this shape that we've drawn to tell us which order to fill them in. So our first line is going to go through the 1s. I'm going to put a star so we remember to start with this one. We follow the line all the way to the end, to the left side of the shape, and then we move back to the right side and drag it down again. So I'll just indicate that by putting a box. Go move from this box back to the top right of the next line, and then follow it down. So our order is going to be through the 1s first, and then the 2s, and then our diagonal lines will start to hit more than one letter. So then the 2p, and then the 3s, and then the 3p, and then the 4s, and then 3d and 4p and 5s, and 4d and 5p and 6s, and 4f and 5d and 6p and 7s, and 5f and 6d and 7p and 8s. And so if you follow that list that I just read off, it should match this experimental filling order. So this is one way to help you remember which order to fill the orbital. So if you want, you can write that at the top of your test or the top of your worksheet to help you remember what order to use for some of those larger atoms. Anything past 3p, anything bigger than argon, you will need to start remembering that filling order. But so for these smaller ones with 18 electrons or less, you won't need this tool. That's one option. There is another option that I would argue is better because it doesn't involve writing out that list of things, a list of orbitals every time you use it. Because it involves something that you should already have lying around, which is your periodic table. So I'm just going to draw a rough periodic table here, and we can use that to talk about this. There's my S block, this is my D block, and my P block on the right side, and the F block underneath. So this time we're actually going to include the rows, and so this darkened line over here is going to indicate where we're going to jump down into the F block. So remember that this is the S block over here on the side. So each row, each period represents a different shell S block. So there are 7 rows. We've got the 1s, 2s, 3s, 4s, 5s, 6s, 7s represented. Over here are p orbitals, and the p orbitals start with 2p. So we've got 2p and 3, 4, 5, 6, 7. Our D block is in the middle, and the D block starts with 3, shell 3, so 3D, 4D, 5D, and 6D. And then down here in the F block, F starts with 4, the 4th shell. So we've got 4F and 5F. And so you have a periodic table, unlike me, so you can use this tool when you're trying to remember the experimental filling order. All you have to remember is where to start and which direction to move. So we'll start here at the 1s, like we have before. So we move to the 1s, and then we run out of things. So we're going to start again on the next row with 2s, and we're going to go all the way across. So we move from the 2s over to the 2p, and then we need to start the next row. So 3s, and across to 3p, And then we run out of rows, so the fourth row is 4s. And this is where it starts to become easier than drawing the list, because you can clearly see as you move across the table, we move from 4s to 3d to 4p to 5s to 4d to 5p to 6s. This is one of the tricky parts. We have to remember that there is this little diversion here where this is where we insert the F block into the periodic table, but so that it's not 18 miles wide, we have just drawn this line, indicated where we took it out. So from the 6th row, we jog over to the 4F, and then we go back to 5D, to 6D, 6P. We start the next row, 7S, and again, we jog down here to the F block, the 5F, then we go back to 6D and to 7P, and if there was an 8S, we would do 8S, but no elements have been discovered that have electrons in the 8S orbital as of this time. So the only thing you have to be able to remember to use this tool is you have to remember that the first S is in the first shell, the first P orbital is in the second shell, the first D orbital is in the third shell, and the first F orbital is in the fourth shell. If you can remember that, 1, 2, 3, and 4, then this is going to be a more useful memory tool than this one. But either of these will work. Please do not memorize this giant list of things. Okay, so let's go back to our rules. Follow the experimental filling order. That is what that refers to. And the final rule that we will add to the bottom is exceptions exist. So rule number 4 was essentially a large exception where we talked about how the experimental filling order was a little bit different than what we would have predicted with the Aufbau principle. There are other exceptions. One of those exceptions is that as you're filling these orbitals and you start to get up to the larger orbitals like the D and the F orbitals, sometimes electrons will get stolen from some of the other orbitals and transferred into the D or the F orbital so that they are entirely full or so that they are half full. Rather than filling them in energy order, they will be filled to half or entirely full, leaving empty spaces below. There's plenty of time left in your chemistry career to learn about those sorts of interesting exceptions, so we are not going to go into them. But these 5 rules are the general principle that will guide you through, if not all situations, most situations and most elements that you'll need to work with. Now that we've finished all of the orbital filling rules, we've finished talking about everything in electronic structure, so we can go ahead and check off the next objective in our course objective list. So we're almost finished with the section of the course on atoms. We have now finished talking about electron configuration, and we'll move on into periodic trends in the next section.